tell you this.
You should try and change that now. Switch it on. Can you make the problem understandable?
Yeah, yes, understandable.
Understandable? Come on, you asked so much.
Yeah, but last time you told us how to do the problem after like 45 minutes, you're like, let me explain how the problem like works.
No, it was pretty close in the beginning. The problem will be about as hard as the last one, and it will be, and you'll have to say what are the objects in the instance. You'll have to say what order you're going to look at them. Either you give each one a greedy criteria, and you need to either, if it's non-adaptive, you sort them based on that ordering, or you can have an adaptive ordering. And then you say whether you keep it or not when you take the next best object. Usually you'll take it unless it conflicts with the previous things. And then you want to prove that this works. Right? Everybody remember the steps? The loop invariant is there exists an optimal solution consistent with what the algorithm has done so far. You assume that the fairy godmother is holding it. You give it a name. And then how do we establish this loop invariant? Initially you haven't made any decisions, so the loop invariant is true. And then how do you maintain the loop invariant? You're at the top of the loop, you assume the algorithm has done some things. And you assume the loop invariant is true, so you assume the fairy godmother is holding this optimal solution. Right? We know what she's holding is consistent with what the algorithm has. We know that it's valid. We know that it's optimum. Right? And then you have a paragraph which describes how to change what she's holding into something else.
Did we do running time stuff?
Let me finish my spiel. Then now you have, she's holding something else. You prove that it's valid. How do you prove that it's valid? It was valid. You didn't add any new conflicts. You prove that it was consistent with what the algorithm had done. You didn't mess those things up, and you made it consistent with the new thing. It was optimum. You made it so that it's at least as good as it was, right? And now you've maintained the loop invariant that there exists an optimal solution consistent with what's been done before, right? You can know, if you want to know what and then the last step is getting the post condition. You assume the loop invariant is true. You assume the exit condition is true, and hence you've made a decision about all objects, so you have an optimal solution. So you have a solution, and then the loop invariant says there exists an optimum consistent with that. Well, that must be it, since you've made a decision about all of them. So what you have must be optimum. So that's what you have to say, filling in those little details. Right? As far as running time, the algorithm, what's the running time of doing all this weird converting from changing what the fairy godmother has into something else? What's the running time of that? Doesn't matter because we don't do it. Right? That was a trick question. The greedy algorithm, all it does, it's really easy. If it's adaptive, if it's not adaptive, it sorts the objects once, so that's n log n time, and that's the main bulk of the time, right? There may be some extra time in checking to make sure that you're not introducing new conflicts, you're not introducing new cycles of stuff. But we're just not going to worry about it, right? If it's adaptive, you have to every time you have to update the priority queue, but it's so small that we just don't worry about it. Greedy algorithms are fast. Everybody kind of understand those things? Now all you have to do is repeat what I said verbatim, filling in the details as necessary. Right? The only other trick is I might ask you, I might give you a possible greedy algorithm, right? And you then have to prove that it doesn't work, right? How do you prove that a greedy algorithm doesn't work?
Counterexample.
One counterexample. You give me one input in which the greedy algorithm does something and it's clearly the wrong answer, right? And as a general rule, if you're finding counterexamples, don't give me big, ugly counterexamples. You know, you can have a counterexample that has 2 or 3 objects, and it's, you know, give me the simplest counterexample. You know?
You don't want to do a lot of work.
Don't make me work. Everybody got that? No code, no proofs of problems that I've already given you.
Is there going to be anything like the last test where at the end you had some question about how many possible games of chess could be played on a board of infinite size, or?
Well, that problem will not be on there.
Will there be something of a similar?
No, yeah, there's just this one problem.
So there isn't craziness out there.
No, there's no craziness. Yeah. Yeah.
We get 2 hours to do a half-hour test. I think this was asked before, but on the final exam, are we going to have, you know, like 4 half-hour questions that we get to do in 2 hours, or?
Yeah, people asked us just as we were leaving, so everybody might not have heard it. And you know, I don't have a good answer for that. You know, the hope is, one, you'll all be experts at doing these, and so you'll do them faster. And then the other, you know, I'd like to stretch the time beyond the, so legally I'm not allowed to set an exam that's longer than 3 hours. I mean, that's just one of the rules, right? Have I had people stay for 5 hours because I didn't throw them out? Yes, I have. Right? Will we be able to do that? You know, probably not. You know, when you have a late exam, you know, and you go to midnight, you know, only the custodians yell at you, and periodically you get a letter from the dean, which I have gotten, that, you know, it's not safe to let you guys go home at midnight. But if it's, the exam is actually at 9, right? So the chances are there's an hour break between it and the next exam in the room, right? So maybe we can get, you know, we could use 45 minutes of that, but the next class is going to want to get in. The only other alternative, which, you know, none of us are going to want to do, is we could show up earlier, right? You know, let's all think about that. You know, I might agree to show up at a certain time, and any people can come as early as they want, you know, or as late as they want. Any other questions? But, you know, really, people panic, right? People panic about this course, and it's a hard course. But I really believe that I've spelled things out enough that if you trust me and do the things I tell you to do, you can all get 60% on this course. You know, there's really no reason that you can't just pass, right?
So the final, will it have one question on each type of will each field get covered, or will it be, you might not cover one?
The plan is to have a topic on each. There's Unit 0 that has the various math, and we haven't covered those that much. Then there's loop invariance, then there's recursion, then there's a graph theory algorithm, and there's, you know, graph theory, we did network flows and you know, Dijkstra's algorithm. Like, it's, you know, you know, I've always had sort of minimally a trace out those, right? And then there's a greedy algorithm and the dynamic programming algorithm. And I've always put a little NP question, and everybody's always gotten it, you know, not half the class got it wrong. I mean, I put it the easiest question. The NP question is always, did you listen to me at all? Did you have your ears open and get, you know, minimally, right now, if I say NP complete, a problem is NP complete, what does that mean? You should already know what that means, right? Unsolvable? No, it's not the halting problem, right? You can solve it in exponential time, right? But But we don't have exponential time, right? We only have at best, 82 or 3 years on us here, right? So, all right. So, what we're talking about in dynamic programming is we first do recursive backtracking, right? I have my instance, and I want to know the best path from S to T. And I can pretend that a little bird tells me to come down here, and I trust her. And then I know that all I need to know is the best path here to here, and I can recurse to get that because it's a smaller instance to the same problem. Why is it smaller? It's because it's a layered graph, and we don't have to worry about cycles and weird things, right? My friend returns this answer, and I tack on this, and that gives me the best answer to my problem, right? It's the solution from path from S to T of those consistent with this first bird answer, right? Then we repeat that for each of these edges and take the best of the best, right? That's recursive backtracking. Why is it? It's because we try something, we recurse, we don't like it, we backtrack, we try something else, we recurse, we backtrack. Recursive backtracking, right? Problem with recursive backtracking is it's exponential time, right? But, are there big computers out there banging out doing this? Yes, they are, right? In fact, I bet you most of your computer dollars out there are doing this, right? Now, we want to turn this into dynamic programming. And how we do that is we assign one guy to handle each subproblem. So there's the subproblem of getting from here to here. And so we want to say, what is the set of all subinstances that are going to arise? We think about, right, we imagine running a recursive backtracking algorithm. What subinstances are ever going to come up by me, my friends, my friends' friends, my friends' friends' friends, right? And we kind of guessed what they were. Last class, we guessed that they were this, for every node, we want to know how to get from that node to T, right? Because everybody wants to go to T. And so then, we need that we have the following properties. We need, just like in a wedding, you need to invite the bride and groom, and you need to make sure that if you invite somebody, you invite their friends, and you need to make sure that you don't invite somebody completely off the street, right? So that's what we're saying here, is my instance needs to be solved, right? That's why we're doing this whole thing. We also close under the friend operation. What does that mean? Well, if this instance is in my set, how to get from V3 to T, then who are his friends? These are his friends, how to get from here to here, how to get from here to here. They also need to be solved, right? Because if he's going to be solved, you have to solve them first, right? And the last requirement only is to sort of save in time. Don't put dumb things in that don't seem to be needed, right? This guy's needed. Why is he needed? Right? Because he's going to come up. Right? Does that make sense? So this is our fine set of subinstances. And then, once you decide what the subinstances are, you want to solve them in an order such that nobody has to wait. And what order is that? Bottom to the top, smallest first, right? Because one thing that we say is that your friends are smaller, right? So if you sort them from smallest to largest, then that's going to be a good ordering. But you know what that ordering is? Sometimes you have to think about it, right? So who goes first? This guy goes first, right? You first ask, what's the, first you do the base cases, right? What's the best path from T to T? And who goes last? It's me. I go last. In some ways, it's kind of like that joke of why is the thing I'm looking for always in the last place that I look? Well, because you stop when you find it, right? So that's kind of like this. The reason this is last is because once we've solved the problem, we're done. All right, so let's now trace out an example of how this is done in dynamic programming. I think this is what we're doing here. You start off by saying the best path from T to T is the empty path with no weight, and then the best path from here to here. These are pretty easy to get the best path. There's only one edge, right? And now we say, what's the best path from here to here? Well, we try coming down here. We ask our friend for the best path here. We combine these, and this gives the best path from here to here that goes through this edge, right? And then we do the same thing to get the best path from here to here that goes through this edge, and then we take the best of the best, which is that. Everybody got that? And then we'll come over here, V4. How do we get from here to here? The bird says come over here. Our friend says this is the best path. We combine them, this is the best path from here to here that goes through this edge. And we do each of these cases, and we take the best of those. Right? Everybody good? And then we come up to the next one. We try each bird answer, and we take the best of them. Get from here to here. We try each bird answer, and we take the best of them. Get from here to here, we try each bird answer, we take the best of them, right? And now it's my turn, right? And now we're going to do exactly what we did in the recursive backtracking algorithm. I want to know how to get from here. I ask the little bird says, come over here. The friend says, this is the best path from here to here. We combine them. This gives me the best path for solution to my problem that goes through this edge. It's consistent with this bird answer. We try each of them, and then we take the best of the best, and we're done. Everybody get dynamic programming? So, now what data structures are we going to use to store all these things in? We need one square. We're going to have a table. In fact, you may have heard one, at some point in your life, dynamic programming is you filling in this table, right? And so what's the table is for every subinstance that you need to solve, you have a square, a cell on which you're going to put its answer. All right? So this question right here is what is the best path from V6 to T? Right? And now when you're giving me an answer on the test, one thing that I really want is I want to be clear about what all your subinstances are and how they relate to the table. I see this, I want to know this is the best path from V6 to T. Right? What's this? The best path from T to T. What's this? This is the best path from S to T, right? How do we fill it in? We just fill it in, right? Does that make sense? Right? How do you fill in this one here? Well, it's the algorithm that we talked about, and all your friends are going to be down. It solves already down here somewhere, right? So if anything, the loop invariant would be. I'm trying to fill this one in. The loop invariant is all your friends have already done their job.
This seems like a lot faster than the greedy stuff, so why would you ever want to do the greedy stuff?
It's not faster. We'll get into timing. Well, in this case, it really is greedy. We'll get into some harder dynamic programming, right? Yeah, maybe the easiest dynamic programming is the same speed as greedy, but we can get really hard dynamic programming. All right, so one thing that I always have a hard time with is knowing what it is you guys aren't getting, right? And after one test, I had a sense that what people weren't getting was what I'm going to do now, so I immediately made these slides. All right? So there's a difference between recursive backtracking and dynamic programming that has to do with how the friends talk to each other. All right? Here, how do they talk to each other? Recursive calls. Right? Here, how do they talk to each other? Through the table. All right? So, as I said, I probably took this for granted before, but now we're not. All right? So, in recursive backtracking, Mr. I here needs to solve his problem, and he's going to ask Mr. K. Right? So, the algorithm is Mr. I here is going to do a recursive call asking about the ith instance. right? This guy's going to go off and solve it, and it's going to get stored up here. And and when he calls it, Mr. K then, this guy is on the stack. Mr. K then solves it somehow, returns the answer, and it goes back up here. Everybody got, that's your standard recursive calls. Now here it's slightly different. K goes first. K finds the answer and stores it in the table. And I just gets it out of the table. All right? People see that? So we're no longer doing this. We're doing this. Right? And then, so this is a typical line down here. Right? The typical line says, my solution that's consistent with the kth bird answer. Right? What is it? Well, I get the optimal solution for my kth friend, and what's that going to be? That's a path from k to t. Right? I add on to it the bird's answer. I'm trying to go from vi to t. So the bird tells me to go first from vi to vk. So I go from vi to vk, and then follow this path from vk to t. Does that make sense? So this is the kind of line that you're going to have to figure out. In fact, most of the code will be the same as my code, except for little lines like here, like this, that do all the work. All right, so here's the dynamic programming code, and as I say, more or less, this is what your code should look like. First step is, be clear about what the input is. Be clear what the solution is. Be clear what the costs of the solutions are. And then you need a table. All right? And so, quite frankly, the table is one of the hard parts to know what your table looks like. So, what I've always done in the past, and chances are what I'll do, again, is I'll say, here's the problem. Now, the question A will be, tell me the bird and friend algorithm. And what will that be? Oh, I'm looking for a path from S to T, so I ask the bird, what is the first edge to take? She tells me to go from S to VK, because the bird answer is always VK. My friend tells me how to get VK to T. I combine them, I get my answer. Right? That kind of thing. So you do that. And then either I'll ask you the B question, or you'll have to do it on your own. You'll think, what is the set of all subinstances that arise? Right? And you'll say, oh, there's a subinstance for every node. For every node VK, I had to get from VK to T. Right? And then you might think, okay, now what order do I fill in the table? Where do I put? How do I structure that into a table? Right? Well, I have one subinstance per node, so I might as well have a one-dimensional table indexed by the names of the nodes. Right? So this line is actually pretty hard, right? Because and you need to be very clear about what this is doing. Right? Optimal solution I stores the optimal path from VI to T. Right? There's a lot of information there, right? This is telling me what the ith entry, what the problem is. The problem is, what is the optimal path from VI to T? And here we're storing the optimal path, and here we're storing the cost of that path. Everybody got that? So that's a bit of a hard line there. And one thing I always look for when I'm marking is if you have question A gives me an algorithm, a bird answer, bird friend answer, and question B tells me what the set of subinstances is. And then I go to the code and I look for a table. And if your table doesn't match what you just said in B, then I'm upset. Right? And you don't want to make me upset. You know what I'm saying?
What if you're like, I'm not too sure about your table?
Yeah, in some ways, here's a question. Would I rather it wrong and then right, or right and then wrong, or wrong and wrong? In some ways, I'm looking for consistency, right? Because if you have different answers on different pages, want to make me think, why? right? Are you not understanding things? Or did you copy from somebody? Or what, right? So consistency is something I like. So I would almost write the wrong answer consistently than to have the right answer in one place. Right? Almost. Yeah, maybe even for sure. Right? Because at least I understand what you're doing. Right? Okay. So that's what, be clear what the table are indexed by and what your sub-instances are. Clear what the sub-instances are. And then the code, you come down here, what the code, skip the base case if you want. I usually skip the base case at first.
Do you have two arrays going on, like a cost array and a solution array?
Yeah, we'll talk about that later, but right now we have two arrays. Or you could think, if you're a big Java person, you could have one array with two fields in each square, but, let's not get scary. I like to have these concrete arrays. And we are going to be changing these momentarily, so. All right. So then, what are we looking for? Is we're looking for that you're looping over the sub-instances, right? Well, here you solve the base cases on your own. That's pretty easy. And then you loop over all the sub-instances. And look at, we're looping from, you have to be clear how you're looping. In was thought to be T, right? And we're looping kind of backwards. So make sure you're looping in the right direction. And then I want to be clear what instance you are working on right now. Right? Right now, I'm not wanting to know, how do I get from VI to T? My goal is to fill in the I table entry. Right? That's my goal right here. Everybody got that? I'm trying to figure out how to get from VI to T optimally. So what I do is I ask the bird for the last edge, the edge coming out of VI. I say, I'm a VI bird, what do I do next? She tells me, well, actually, she doesn't tell me anything. We loop over all her possible bird answers. You think, what are the possible bird answers? I really like this. You say here, percentage mark, that means comment. I'm looping over the sub-instances. Here I am doing it. This is what the sub-instances I'm now working on. Right? I am now trying every bird answer. Here I am doing it. Watch me. And now, which one am I currently working on? Right? If I can see those, man, I can mark this fast. Right? I see what you're doing, bang, 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 check, we're on. Right? So, here is just, so what answer is she giving? Right? She says go from VI to VK. Now, this paragraph here, I do want to see this paragraph, but I only need to see it once. Right? If I ask for it in question A, don't give it to me again. Right? Waste your time and waste my time. Waste your time more, because I'd skip over it. Alright? But what is the bird algorithm, right? The bird tells us that the first edge in the optimal path from VI to VT is VI to VK. We asked our friend for the optimal, alright, so that's what we asked the bird, right? Then, what do we get help from the friend? The friend tells us the optimal path from VK to T, right? Where do we get the optimal path from VK to VT? We get it from the table, right? So I see this here, I see it in the code, right? He gives us the optimal solution. There it is, the optimal solution, which he stored in the table. To this, we add the bird's advice. Right? So everybody's following this? The optimal solution from VI to T, consistent with the kth bird answer, goes from VI to VK, because that's what the bird told me to do, and then is an optimal path from VK to T. Everybody get that? Is anybody not following that statement? Because that's crucial. Alright? Then we compute the cost. What's the cost of my path? What's the cost of my friend's path? Plus the cost of this last edge. Right? Actually, it's the first edge. After we've done that for every bird answer, then I'm still looking for the best path from VI to T. I have the best, for every possible bird answer, I have the best answer to my problem consistent with that bird answer, and I figure out which one is best. Right? So this is either minimize or maximize, depending on what our problem is. Right? And then I store in the I table entry, I store those optimal solutions and their costs. Everybody got that?
I still don't understand why there's a bird. The bird doesn't do it.
Then don't have a bird. We'll be talking about birds later on and how I like to think about birds, but the main reason is, for me, is that we have a dialogue we're talking about. You could call them things that I try, and now I'm trying this. You could call them a bird answer. It's just, they're words. Then you do the base, you have to know what your base cases are. And now in the end, right, this is not recursive. Right, so make sure you don't give me recursive code. This is not recursive. And at the end, you just return the answer. And where's the answer? It's stored in 0 because 0 is thought of to be as S. So this is the best path from S to T. Right? Now, let's just make our life a little bit more complicated. We just keep, everybody good so far? We're going to just change things slightly. If you look at this last code, there's something kind of odd about it. And what's odd about it is we start at T and we kind of move backwards. Right? We're moving backwards through the graph. And is there any problem with moving backwards? No. There's only thing that in this next slide we're talking about is aesthetics. All right? People don't like moving backwards, they like moving forwards. Now the problem is that we start with the recursive backtracking algorithm, the bird answer, the bird problem, in the recursive backtracking algorithm. And when we turn it into dynamic programming, we turn it upside down. Right? So if you don't like your dynamic programming algorithm upside down, how do you get it to be right side up? Is well, you start off with your recursive backtracking algorithm being upside down, and then when it turns upside down, it's actually right side up. Right? Does that make sense? So, as a general rule, when you think, the first question you should ask is, I have this instance, how do I get it from a path from S to T? What should I ask the bird? Don't ask the bird about kind of the first object, ask the bird about the last one. All right? So instead of asking the bird, what is the first edge I take, we ask her, what's the last edge? And if she says the last edge you take is from VK to T, then I ask my friend, what's the best path from S to V6? Right? And I combine them. Everybody got that? And then I do all of these, and I do the best of the best. And now you'll note that what are my subinstances? They're all of the form S to something. Right? We all start, instead of we are going to T, we're all starting at S. And somehow, aesthetically, that looks a little better. So, determine this complete set of subinstances. They're the best path from S to every node. Right? What's our table? Now our table has a more forward look to it. We start out with the best path from S to S, and we end up with the best path from S to T. Right? Going through S to V2, S to V3, S to V4.
Do you care which way we do it? Like on a test or something?
I think historically I've taken off about 1% if you do it backwards. Yeah. So there's no harm in turning it around. Alright, so how does this change things? Well, our table is now the optimal path from S to VI. Right? The base cases are now from S to S instead of from T to T. We're looping in the opposite direction. The bird tells us the last edge. Here, what is our best path from S to VI? Well, it's the best path from S to VK, and then from K to VI. Right, the last edge from VK to... People see that? Oh, we turn it around. And otherwise, it's the same. Okay, now, everybody good with what we're doing so far? Because we're going to make it a little harder. All right, now we're going to look at running time. What's the running time of this algorithm? What are we looping over here? You can read it. Hopefully you can read it because we've been doing the slides all along. We're looping over the subinstances, right? So the number of subinstances matter, right? If your wedding party is too big, you're going to have a problem, right? We have to solve all these subinstances, and so the number of subinstances that you have is crucial, right? Then what do we loop over? Bird answers. I'm glad you all got it. Then, in this case, we got in subinstances. How many bird answers do we have? Right? D is sort of the degree of the graph. Right? In fact, in the end, this is going to be the number of edges in the graph. Now, so this is something you should memorize, right? The running time of a dynamic programming algorithm is the number of subinstances times the number of bird answers, right? Because you have to solve all these subinstances, and for each subinstance you go over all the bird answers. Everybody got that? So you want each of these to be small, but there's a bug in this. What I'm saying. What's the running time of this line of code? That's the problem. Is it constant? It turns out not to be constant. Let's concentrate on this line of code. What's happening here? What's stored here? An optimal solution. What is an optimal solution? It's a path. What is a solution? It's a path, right? How big are paths? Paths could be of size n. This is an object of size n. What are we doing with it? We're tacking something on, and then we're copying it. How long does it take to copy an object of size n from one place in the table to another place in the table? Takes n, right? Right? This is our friend, gives us the best path from S to VK, and then we copy it over, right? So the time is the size of the path is n. Everybody got that? So that's a problem, right? So now we have that the running time of a dynamic programming is the number of subinstances times the number of bird answers times the size of the solution. But don't memorize this piece because we're going to get rid of it. All right? So how do we get rid of it? This is the line of code we don't like, right? And I don't recommend you doing this. Don't try this at home. But the way we're going to get rid of it is we're going to just get rid of that line of code. All right? This line of code is copying this path around, and right? And if we never copy it, then we should never store it, right? We're just getting rid of that from the code, and let's see what happens. All right? Okay, let's think about how much space is stored. Before we stored for every subinstance, we had to store the entire path, right? But we don't want to do that. For every subinstance, we want to store one integer, right? Here we're just storing. Now we're just storing the cost. All right? All right. So we've just changed the problem from before the problem was give me the optimal path from S to V7, and now the problem has changed. I don't want the path. Right? Path is too big. I don't want to deal with it. Just tell me the cost of the optimal path from S to V7. Right? So how do we solve that? Well, I'm trying to get from S to V7. We ask our bird, what is the last edge that we take? Right? Bird says, take this edge. And then we ask our friend, do we ask our friend how to get from S to V4? No. What do we ask our friend? What's the cost of getting from S to V4? Our friend says 8. So what's the cost of getting from S to V, whatever this is, consistent with this bird answer? We take this 8, we add it to this 2, right? And we do that for each bird answer. And now we know the cost of each of these options, so we're still able to take the best of the best. Does that make sense? So we have these 3 costs. We take the best of the best. I guess it's the 9. So everybody see that we determined the best cost. Yeah, but in the end, are we happy? No, in the end we want the path. So what did we also learn as we did this? We learned which edge, the advice of the bird, right? We learned that this was the best one. We learned that if you're trying to get from S to VI, the answer the bird will give you is this guy right here, right? The bird advice. Everybody get that? So, so what we're going to do is we're going to add an extra line here. Right here we calculate the K that minimizes the cost, right? And what we're going to do is we're going to save the bird advice. Does that make sense? And this is just, before it was a whole path, now this is just a pointer. In fact, it should remind you of when we were doing depth first search and stuff, you'll remember who your parent is. Right? So this is basically what we're doing. Every node, remember who the parent is. So what I should see up here is it says, right, here I'm saying optimal solution I would, if you guys are good at English, that means we're not actually doing it, right? It would store an optimal solution from S to VI, right? But actually, we don't store it because it's too big, right? So actually, we only store the bird's advice for the sub-instance and the cost of its sub-instance, and we store them in these tables. We have a table for bird advice. We have a table for optimal cost. Everybody got that? Right? And this, as you see, gives a nice uniform way of talking about it, right? You're going to always be storing bird advice. You're always going to be storing optimal cost. So just call them that and I will know what you're talking about. Right? The goal is for, in shortest time possible, you convince me that your code is kind of going to work. Right? If you do something completely weird, then we'll both be working harder. Right? And I'm lazy. You're lazy. Alright, so, you know, here we're looking over bird answers. Here we put the best bird answer in. Everybody kind of got what we're doing? Oh, here's another thing. I like it when people put these lines here when they're constructing the sub-instance. When my request is keep those in, but comment them out. Right? And then I'll be double happy. One, I will see that you knew how to do it. And I'll see that you knew to take it out. Right? Can everybody do that? All right, but now in the end, what do we have? We have the costs of the best solution, and we have all this bird advice. So what are we going to do? Is we're going to just do it again. Right? We did it once. We just start all over again and try to solve the problem again. But the advantage now is we have a bird, and the bird's very useful. Right? Now I'm looking for the best path from 0 to 12, and see this little dark arrow here? That's the bird advice. The bird says this is the last edge you should take. Right? So it's really easy for now. I just run the recursive backtracking algorithm, but it's kind of like doing a greedy algorithm where you have advice of the bird. I don't try all these. I go here and I ask this friend. Right? What does this friend say? This friend says, oh, this edge. This friend says, take this edge. This friend's bird says, take this edge. We trace them back up. We're done. 5 minutes. Excellent. Everybody getting this?
So why are we doing another recursive backtracking? Why can't we just look at the table and just construct a path?
Yeah. You can do this recursively, or really you can do it iteratively. Right? You can just follow these pointers back up. It's really, either way, it's really easy.
So I just want to break the table. It says if you go this way, it will tell you how to get from this point to this point. Is that what you're storing, right?
Yeah.
Storing one edge from the previous node to get to the next.
Right, right. It's pointers to the parent. Right? I'm here. It tells me in the best path from 0 to 12, the last edge should go to here. So from here, the last edge goes to here. From here, the last edge goes from here. Here, the last edge here. You know that we, just for free, we know the best path from 0 to V8 is going to be this. right? What we have here is just as we did when we did breadth first search, is we have the tree of optimal solutions. All right, so this is I've never actually been asked for this. This is one. You got a question?
Yeah. How does the bird know which path is the best? Which edge is?
Good question. All right. So I want to bet the best path from here to here. I try this bird answer, right? The friend tells me this optimal cost, right? And then I try this bird answer, and the friend tells me the optimal cost. In each case, I get the optimal cost is his cost plus this edge is the best cost from here to here via this edge last, consistent with this bird answer. So I try all of them, right? And now I know the best path from here to here through this edge has cost 10, right? Because it was the 8 plus the 2, right? And I take the best one is going to be the 9. So the best one is through this edge.
But aren't you saying that the bird knows in advance that the 9 is the best?
No.
Oh, she asks the friends.
No, we do it. We run this algorithm twice.
Okay.
The first time we run it, we have no bird, and we have to try all of these things, and then we store it. We store this bird's advice. So here in the code, we take the best of the best, and we store the bird's advice.
Oh, okay.
Right? That's the first time we run it. The second time we run it is down here. You can't even see it. Right? The second time we run it. See how I moved the slide up a bit? That was very nice of me. Right? Now, this is running the leveled graph with advice. And I want to know the best path from from S to T using the bird's advice. Right? So now we have this bird's advice. She stored it in the table. Right? And now we fill it in really easily. Right? Does that make sense? So you could think about it. All right, so here's a question about what happens if there's more than one optimal solution. I fudged one of these numbers, now those paths are the same length. Right? What's the code going to do now? At what line in the code, right, is this going to happen? Right? She says, which is the last edge do you take? Right? And she could give you either answer. Right? It's kind of like there exists an optimal solution consistent with this path, right? And so we try the. Oh, sorry, everything's flipped upside down. Ignore that. When we find the best path for each of these, right? Oops. At some point we say, oh, these paths have the same value, and we get to choose which one they are.
So the choices happen in front first. And once the bird knows all the paths, the choices.
Yeah, once we tried all of these,
Yeah.
then we take the best of the best, and we note that they're two to the same.
So it'll happen up there.
It will happen in the code. Take the k that minimizes these. Right? Take the